In southern India, a massive construction site spanning thousands of hectares is operating at full capacity. Hundreds of heavy industrial machines and thousands of workers are digging directly into the riverbed to build Polavaram, a mega gravity dam project with a total investment of nearly $7 billion. To give you an idea of the project's scale in today's video, its concrete spillway structure is over 900 meters long, designed to handle a flood discharge volume of up to 5 million cubic feet per second. But for the engineering team, casting a massive concrete structure across the Godavari River is just the surface of a giant mechanical problem. What truly concerns them is not the size or length, but the physical pressure. A massive thrust carrying the phenomenon of flow cavitation, always ready to break this reinforced concrete structure from the inside. How do you build a solid foundation system right under a complex riverbed and apply mechanics to completely neutralize the pushing force of millions of tons of water? Before we dissect the mechanical structure of this massive project, don't forget to like and shake up this video, my friends. And now, let's get right into it. The Polavaram project in Andhra Pradesh state has a long engineering history. In fact, the idea of setting up a gravity barrier across the Godavari River was drafted in the 1940s. However, it took decades for mechanical technology and construction capabilities to match its massive scale. For a long time, due to the lack of a mechanical defense system, the enormous kinetic energy of the Godavari River during the monsoon season directly converted into an extremely strong erosive force. The high-speed flow continuously stripped and collapsed both riverbanks, tearing apart natural boundaries to directly discharge millions of cubic meters of water, flooding the entire coastal downstream delta of Andhra Pradesh. Meanwhile, in neighboring basins, hundreds of thousands of hectares of land were completely barren due to water shortages. Restarting this project carries a complex mechanical mission, establishing a massive barrier to control natural water pressure and redirecting billions of cubic meters of fluid through the east-west canal network to the Krishna River basin. This system will provide a stable irrigation water source for 720,000 acres of farmland, while creating a high-pressure flow that supplies kinetic energy to a 960 megawatt hydroelectric power plant. To make this mega project a reality, the first mechanical challenge was not located at the bottom of the river, but on the riverbank. Engineers excavated a massive approach channel on the right bank, where the geological foundation is most stable. This was a mandatory hydraulic stepping stone in preparation for the river diversion process. Right on the dry ground of this channel, the concrete spillway superstructure was prioritized for casting. At over 900 meters long, it acts as the vital discharge valve, designed to bear an extreme flow rate of up to 5 million cusecs. Additionally, this dam mass integrates a 250-meter-long fish ladder to maintain the migratory cycle of the aquatic ecosystem. The construction process of this architectural mass required unimaginable intensity. In 2019, the project set a world record by continuously pumping 32,100 cubic meters of concrete in just 24 hours. However, at this massive volume, the curing process generates an extreme heat of hydration reaction, threatening to fracture the structure from within. To neutralize this mechanical risk, the aggregates had to be cooled using flaked ice from on-site production plants, forcing the material mass to maintain strict standard temperatures until fully hardened. Once the onshore spillway was completed, acting as a safe discharge valve, the barrier system known as cofferdams was officially established to lock down the main river channel. On the upstream side facing the flow, a 2.3-kilometer-long upstream cofferdam was erected. This is a superstructure 41 meters high with a base width of 145 meters. Its mission is to directly withstand the kinetic energy of the river crashing into it, forcing the massive volume of fluid to divert and flow through the spillway. At times, this barrier has to brace itself to hold back up to 120 billion cubic feet of water. On the downstream side, 600 meters away, a 1.45-kilometer-long downstream cofferdam was also established, serving as an absolute mechanical seal against the backflow of pooled water. With both the inlet and outlet locked down, the old riverbed was completely drained, exposing the river bottom to begin work in the deep geological layers. Challenge is revealed: groundwater. The riverbed of the Godavari is an extremely loose, porous layer of sand and mud. The pressure from the massive amount of water blocked outside will force the current deep underground, leaking through the sand and flooding directly into the foundation pit. To cut off this underground leak, plastic concrete diaphragm wall technology is deployed. Giant hydraulic trench cutters dig trenches up to 100 meters deep through the sand to reach the solid bedrock. During the excavation, bentonite slurry is continuously pumped down to maintain pressure and prevent the trench walls from collapsing. Next, a plastic concrete mixture with a specially adjusted ratio of cement and bentonite is pumped in to replace it. Unlike regular stiff concrete, this material has mechanical elasticity. It allows the wall to bend and settle naturally with the ground under massive water pressure without cracking. However, during the 2019 flood season, the river's kinetic energy exceeded the design limits. It created severe erosion holes beneath the riverbed, generating a twisting force that broke a section of this underground wall. The engineering team was forced to dig deep and cast a second parallel wall. This created a solid double-wall system to block all underground water, clearing the way for the dam's foundation to officially rise above the ground. Once the foundation is securely locked, the 2.5-kilometer-long earth core rockfill dam is built. This is a strict, mechanically layered structure, a tightly compacted, waterproof clay core, sandwiched between sand and gravel filter layers, and surrounded by a reinforced rock shell. This outer shell acts as a load-bearing base, directly breaking and absorbing all water pressure. The only mission of this dam is to completely block the main river. As the rock-filled dam blocks the river, the entire water flow is forced toward the concrete spillway on the right bank, a superstructure whose rough construction was already completed. Here, the final mechanical component is integrated. A system of 48 steel radial gates is installed. Each gate is 20 meters high, 16 meters wide, and weighs hundreds of tons. They are operated with absolute precision by high-capacity hydraulic cylinders. These massive gates work together with a giant stilling basin at the foot of the dam. Here, water falling from tens of meters high is forced to crash into stepped baffles to destroy its energy. This prevents the destructive effects of cavitation and protects the concrete surface before the water is safely discharged downstream. Meanwhile, the kinetic energy of the Godavari River is captured to the fullest. Located separately on the left bank, the Polavaram Hydroelectric power plant is operated by 12 Kaplan turbine units, each with a capacity of 80 megawatts. Under the force of water pressure, the flow is compressed and pushed through giant steel penstocks, 150 meters long and embedded deep into the rock. This water directly spins the turbine blades to generate a total power output of 960 megawatts. Finally, the fluid distribution system operates through two giant canals. The 174-kilometer right main canal transports water entirely by natural gravity flow to the Krishna River basin. Meanwhile, The 181.5-kilometer left main canal takes on the role of providing a high-capacity industrial water supply to steel mills and industrial zones in Visakhapatnam city. In conclusion, the $7 billion Polavaram mega project is not just a simple physical barrier. From the underground wall system resisting twisting forces, the pressure-absorbing dam, and the world's largest spillway to the power-generating turbine system, everything is linked into the largest fluid control and dynamics transformation machine ever built in India. Despite facing the devastating mechanical forces of nature, the creation of this machine is an absolute proof of human engineering calculation and mechanical power. Thank you for watching this anatomical breakdown of the Polavaram mega project. Hit the subscribe button to continue dissecting the mechanical structures of the world's most massive mega projects. See you in the next project.